And the four variable Kamaugh is like this. And we must know the first row and the last row. The first row and the last row is adjacent, and the left column and the right column are also adjacent to each other. Kamaugh SOP minimization or minimize the SOP expression contains the few is possible terms with the few is possible variables per term. So we must remember that the few is possible terms and the few is possible variables per term. These 2 points are very important. Mapping or standard SOP expression from Kamaugh is very easy. The first step is determine the binary value of each product term in the standard SOP expression, and then place a 1 on the Kamaugh in the cell having the same values of the product term. So for this Boolean expression, we first write down the binary value of each product term. 001, 010, 110, 111, and then write down there on the Kamaugh. Place 1 on the Kamaugh for corresponding cells. For our non-standard SOP expression, it is a little complicated. First, we must convert the non-standard SOP expression to a standard form. For 3 variables, AB bar is equal to AB bar C plus AB bar C bar. So there are 2 standard SOP expressions, 2 standard SOP product terms. If there are 4 variables in the domain, then there are 4 product terms, 4 standard product terms. A, B bar, C bar, D bar, A, B bar, C bar, D, A, B bar, C, D bar, A, B bar, C, D. So there are 4 standard product terms. For this expression, it can also be converted to a standard SOP expression, and then place 1 on the corresponding cells. And Kamaugh can also be used to simplify on SOP expression. So we must remember the grouping rules, grouping the ones rules. A group must contain either 1, 2, 4, 8, or 16 cells. So 1 is 2, 0, 2 is 2, 1, 4 is 2, 3, 8 is 2, 3, 4 is 2, 8 is 2, 3, 16 is 2, 4. So they are all powers of 2. That is the first rule. The second rule. The second rule. Each cell in the group must adjacent to one or more cells in that same group. But all cells in the group do not have to be adjacent to each other. One or more cells are adjacent to the cell, but all cells in the group do not have to be adjacent to each other. It is obvious. And rule C always includes the largest possible number of ones in the group, in accordance with rule 1. The largest is very, very important. So, if there are eight cells are adjacent, we cannot group for ones. We cannot group for one because the largest possible number is 8, not 4. So if there are four ones are adjacent to each other in the group, we must divide the 4 ones into one group, not 2, because the largest possible number of ones is 4. For this column map, the 4 ones are in one group, and the first row and the last row are also in one group. That is rule C. Rule D, each one of the maps must be in at least one group. So everyone, each one must be included in at least one group. The ones already in a group can be included in another group, as long as the overlapping groups include non-common ones. As long as the overlapping groups include non-common ones. So for this column map, there are two groups. Two groups. The second group is not necessary. We can ignore this group because for the first group and the third group, all the ones are included in at least one group. So the second group don't need to.
So this green one is no need.
Yeah.
Yeah.
Good. There are also two groups. Also, or three groups.
One.
Because there are 5 ones.
Yeah.
5 ones.
One adjacent and one on
Yeah.
this last row.
And there are two ways. There are two ways to group this one. The first method is the left column map. The second is the right column map. The difference is the one in right down corner, in right down corner cell. This one can be grouped into this group, or can be divided into this group. So there are two ways. There are two ways to group the one. And after grouping the ones, then we can determine the minimum SOP expression from the grouped column map. Each group is corresponds to a product term, and if in the group all the variables occur either uncompleted or completed, for if a variable is 0 and 1, then the variable must be eliminated. So for this group, its corresponding product term is please see the PPT. For this group, because variable A occurs in 0 and 1, so A must be eliminated from the product term. B always 1, so B must retain. And C occurs with 0 and 1, so C must also be eliminated from the product term. So it's this group, the corresponding product term is B. For each group, we must determine the corresponding product term. When all the minimum product terms are derived from the Kamaugh, then they are summed to form the minimum SOP expression. For this Kamaugh, there are two groups. Each group has one product term. So for this group, what is the corresponding minimum product term? A bar. Vincent, what is the corresponding minimum product term for this group? What? A bar. Why? Why?
This group is common by the table.
Why? For this group, do you find that B occurs with 0 and 1?
The same.
So the variable B must be eliminated. And C also occurs with 0 and 1. So C must be eliminated. For A is always 0. So the product term must be A bar. 0, A bar. So the answer is A bar. The minimum SOP expression is A bar plus B. for this Kamaugh, there are three groups. What is the minimum product term of this group? Shihapu. A, B. B.
One.
Yes,
B.
very good.
It's not changed,
Yeah.
right?
Still, this group, for A, it occurs with 0 and 1, so A must be eliminated. B equals 1, yes?
C.
But
Also C.
C,
Also C.
C, C always
One.
1, so what is
BC.
the minimum product term?
BC.
Yeah, BC. B always 1 and C always 1, so the product term is C. Oh, and what is the minimum product term for this group?
For this group, it changes.
This group. A. What? AB bar.
Full group. Which
Yeah.
group, sir?
Very good. Summing, very good.
Sir.
AB bar.
Also loud like a pussy.
For this group,
But
for
sir,
this group, A is always 1, B is always 0. So A, B bar.
But sir, I got.
And C always 0 and 1. 0 and 1. So the corresponding minimum product term is A, B bar. Okay, listen. This one for this group. What is the minimum product term?
B bar.
Do you find the reason? The reason for this two cells, A,
It
what
changes.
is 0 and 1.
Eliminated.
B,
0.
always 0. C,
Always 0.
always 0. So the product term is, yeah, very good. B bar, C bar. So the SOP expression, the minimum SOP expression for this Boolean expression is this. If we use the second grouping method, then the minimum SOP expression is the other. So we now understand how to simplify a Boolean expression to a minimum SOP expression. Use the Kamaugh. Then, if we know the truth table, we can also map in the truth table to a Kamaugh. For example, for this truth table, we first find the output whose value is 1. And they write down the 1 to the corresponding cells.
First one. Yes, sir.
Yeah. So there are 4 1. we have learned the Boolean expression, the truth table, the color map, and the logic circuit to describe all logic functions. And the fifth way description of the logic function is just on text. Is just on text a description. So we just need to know the first four ways. Boolean expression, truth table, color map, and logic circuit. And don't care conditions. Don't care conditions. Don't care is a very important concept because we can use don't care to simplify a Boolean expression. It can be regarded as 1 or 0 or 0. For this example, BCD code. If the BCD code is 7, 8, or 9, then the output is 1. The output is 1. What is the simplest? What is the minimum SOP expression? Then, for BCD codes, the inputs do not include the 6 combinations. The 6 combinations are not included in the BCD code. So the output is 8. It is X represent don't count because the 6 inputs are not allowed. So on the color map there are 6 X and 3 ones. If we use the don't count condition, the output is very simple. The output is the minimum SOP expression is very simple. A plus BCD. If we do not use the don't count conditions, the output is a little complicated. A B bar C bar plus A bar BCD. So we must use the don't count condition. Okay. Chapter 5 evaluation and Combinational logical analysis. There are two diagrams, two symbols, two kind of symbols to represent our Boolean expression. The left is the logical diagram, standard distinctive shape symbol. We like this method more. And the right symbol is an ANSI standard rectangular outline symbol. I like this more. In some of the products from basic combinational circuits can be directly implemented with and or combinations if the necessary complementary terms are available. For the Combinational logic circuit application, our storage tank monitor. We know that for this monitor, if if any tank are empty, the output is low. We have learned this last time. And or in what logic, when the output of SLP form is inverted, added on inverter, then the circuit is called AND or invert circuit. AND or invert circuit. The AOI configuration lends itself to product of sounds implementation, POS implementation. Excludes all logical. Excludes all means the output is high whenever A and B are unequal. If A equals to 1, then B equals to 0. If A equals 0, then B equals to 1. So the output is 1. We call this logical. Exclusive or logical. Exclusive or.
When this two is opposite, output is high.
Yes. We must remember this symbol. And this symbol. Both the two symbols represent the exclusive or logical gate. Exclusive non-logical means that the output is high whenever A and B are equal. If A equals 0, B equals 0, or A equals to 1, B equals to 1, then the output is 1. So we call this logic on exclusive non-logical. And the diagram for exclusive non-logical is like this. We only need to add an inverter to the output of XOR, exclusive or logical. This logical is on XOR. Logical. And the output, the expression is A bar, B bar plus AB. It is different from the XOR logical. For XOR logical, the expression is X equals to A bar B plus AB bar. On exclusive non-logical can also be used in the data transmission with error detection. For this diagram, the first, the up part is a parity generator. There are 4 bits. The default is 4 bits. A1, A0, A1, A2, and A3. 4-bit dates are inputted in the 4 inputs. And then A0 and A1 are XORed. A2 and A3 are XORed. And then the output of the 2 gates are XORed to generate on even parity bit. If there are even ones in the date in the 4 bits, then the output is 1. You know? A0 XOR A1 and then A2 A1 A3, right? So if A0 and A1 are unequal, then the output is 1. If A2 and A3 are unequal, then the output is also 1. So when there are even number of ones, then the output is 1. We must construct the truth table. A3, A2, A1, A0, and Y output. Y represents output. A3, A2, A1, A0, Y. 0, 0, 0, 0. 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1. For this input, 0 XOR 0 equals to 0, right? 0 XOR 0 equals to 0, so the output is 0. For this input, 0 XOR 1 equals 1. So 1, this is 1. This is 1. And 0 XOR 0 is 0. So 0 XOR 1 equals to 1. Right? Yes. And for this is also output is 1 because the output of these two variables 1 XOR 0 is also equals 1. For this input, for this combination, 0, 0, 1, 1. 1 XOR 1 equals 0, right? 1 XOR 1, because they are equal.
So the 0.
So the output is 0. For this combination,
1.
1,
Yes. 1 and plus 0.
1. A2 XOR A3, 0 XOR 1, 0 XOR 1 equals 1.
Yes.
And 0 XOR 0 equals 0.
So this 0
So
and 1.
0 XOR 1 equals 1. Right?
0, 1, 1. This 0.
0.
Yes.
Do you find the rhythm? The pattern, do you find the pattern? X 0 XOR 1 equals 1. 0 XOR 1 XOR 1 equals 1. 1 XOR 1 equals 0. This
0.
1 1
0.
0. For this
1.
1 0
1.
1. So we know that 1 0 0 0 1 0 0 1 1 0 1 0 1 0 1 1 1 1 0 0 1 1 0 1 1 1 1 0 1 1 1 1. The output is I have found the pattern. I know that if there are even ones on the combination, the output is 1. Right? So the output is for this combination. For this combination, the output is 1. This
0.
2 ones.
0.
2 ones. So the output is 1. 2 ones.
0.
0. 3 ones. 3 ones.
One.
So the output is 1. 2 ones. 0. 3 ones.
1.
1. 3 ones.
1.
1.
0.
4 ones. 0. So this bit. So this bit is on even parity bit. Even parity bit. When the dates are transmitted by the transmission media to the terminal, the date bits must also the output, the even parity bit must also the same. If the output is wrong, then the indicator will that is the transmitted wave. The output is the even parity bit on the of the terminal or of the receiver, and this even parity bit is the parity bit of the transmitter. The output of this is the parity bit of the receiver. These two bits are XOR. Then, if the two bits are different, then we know that the date had an error. Do you understand? Because from the transmitter. The data bits output of the eventuality is 1. And when the receiver, on the receiver, the output of the parity bit is 0. They are different. So the data is error, has error. So this is exclusive. The exclusive non-logical can be applied to the data transmission with error detection. Okay, have a rest for 10 minutes. It's done by first forming the end term, then the terms are all together. So it's very easy. If we know the SOP expression, then we can get the delta like this. For this truth table, if we know the truth table, how to get the delta or the circuit logic? We must first find the output once. So we know the SOP expression is A bar BC. A bar BC and plus A bar A B bar C. So we must first forming the end terms. So one AND gate, second AND gate, this AND gate. For the first AND gate, the input is A bar B C. So A must be inverted by an inverter. So the output is A bar. And for the second term, A B bar C bar. So B and C must be inverted by an inverter. So the input of this AND gate is B bar, A, C bar. And the two terms are ORed by the OR gate. Then the output is the SOP expression. That is the circuit logic for this truth table. Universal gates. NAND gates are sometimes called universal gates. NAND gates. Because they can be used to produce the other basic Boolean expressions. They can be used to produce the other basic Boolean function. For the inverter, the first basic Boolean function is inverter. If we get the two inputs together, then the output, the function of this gate is equal to the function of inverter. For the AND gate, we use two NAND gates. Can use to generate the AND gate, because this is AB bar, right? AB bar and AB bar double bar. So AB double bar equals ABD. For XOR gate for OR gate, use three can be used to generate on OR gate. It's very easy. A bar, B bar. A bar, B bar, bar. A bar, B bar. Use De Morgan's law. You know that it because A double bar plus B double bar. A double bar equals A bar, B double bar equals B. So A plus B. NOR gate. Just add on NAND gate. So 4 NAND gates can be used as a NOR gate. It can also be used to generate the NOR gate. So we call NAND gates universal gates. NOR gates are also called universal gates because they can be used to produce the other basic Boolean function. Also A bar, A plus B, A and B, A B bar, A B bar. So if if the text represents on term universal gates, we must know that they mean the NAND gate or the NOR gate. Combinational logic can also be used to temperature control. For this diagram is a little complicated. T represents the temperature. It is an analog signal. So we must convert the analog signal to digital signal. So we must use analog to digital converter. Analog to digital converter to our digital signal. The digital signal has 8 bits. Binary code. it is on 8-bit binary code. Then we use binary to BCD converter. Binary to BCD converter. To convert the 8-bit binary code to 8-bit BCD code, and then the 8-bit BCD for specified temperature can be used to control the temperature. We must note that the 8-bit BCD is for specified temperature, and this 8-bit BCD is for manual temperature. The two BCD codes are processed by the temperature control logic. Then the output is on temperature. This is the diagram, the circuit, the logic circuit. There are 8 XOR gates. 8 XOR gates. BCD for measured temperature is A7 to A0, and BCD for specified temperature
B0 to B0.
B7 to B0. They are odd. They are XOR. XOR gate. And then the output of the 8 gates are odd. So we have finished chapter 5. Yes, it's very
Small.
the contents are very easy. The key terms are universal gate, negative or logical, negative and logical.
Easy.
Let us do some exercises.
Yes, sir.
The first is, please see the PPT. Assume an AOI expression is AB plus CP bar. The equivalent POS expression is
A bar plus B bar times C bar plus D bar. B.
B. We must use the De Morgan law.
B, sir.
De Morgan law. Vincent, what is the answer?
B.
First, AB bar and CD bar, right?
Yes, sir.
And then AB bar equal to
A bar plus B
A
bar.
bar plus B bar. So
C bar plus D bar.
C bar plus D bar.
B.
So the answer is B.
Yes, sir.
The truth tip sum is for
AND gate.
AND gate.
No, not AND gate.
Explosive knowledge.
It plus NOR gate.
Yes.
Yes, right.
No.
You're right. Because if AB are equal,
This is
right, the output is 1.
Yes.
So it is the
B.
B on exclusive NOR gate. Exclusive NOR gate is also named XOR gate, right? XOR gate.
X not gate, sir.
Oh, XNOR gate. XNOR gate. XNOR gate.
X or gate.
And the exclusive OR gate
X or gate.
is also named XOR gate. Three. The truth tip song is for
X or gate.
C. Yeah.
C.
C. C. What type of output gate is needed to implement the logic expression? So, later. Complicated. Vincent,
Sir,
what is the answer for this question?
3 input or gate. 3 input or gate.
A bar, B bar, this product term, right?
Yes.
A, B bar, D, this product term. And B, D bar, E, this product term.
3 input or gate.
They are odd. They are odd, right? So the answer is what is the answer?
So we need this output. So we OR gate, sir. 3 input OR gate.
3 put
OR gate.
yeah. 3 put OR gate plus represent OR. Plus represent OR. So they are odd.
C.
The answer is C.
The circuit.
Question 5. The circuit zone will have identical logical outputs if all gates are changed to we have identical logical output if all gates are changed too. It's very hard. It's hard. So we first must know that
NAND gate.
we must first write down the Boolean expression for this circuit. AB plus CD. AB plus CD. So AB plus CD. AB plus CD equals to number one, right? Number one. And then for the first bar, we use De Morgan law. According to De Morgan law, we know that
AB bar
AB bar
dot C bar
dot CD bar and bar. So the answer is
NAND gate.
the answer is AB bar is the first NAND gate. AB bar is the second NAND gate. And these two groups
Also NAND gate.
also use the third NAND gate.
The NAND gate.
So the answer is C.
That's for me.
We can use 3 NAND gates.
Yeah.
Question 6. The expression A plus B and C plus D can be implemented use only. If we direct use the logic gate for this Boolean expression, we know that A plus B is a one OR gate. C plus D is a OR gate. And the two parts are AND, so AND gate.
Yeah.
So 2 OR gates and 1 AND gate.
A.
How to convert it? How to convert the expression to we also know that A plus B and C plus D double bar. And for these two parts, we know that it equals to A plus B bar plus C plus D bar, right? De Morgan's law. According to De Morgan's law, we know that C equals D. So from this expression, we know that all NAND no gate, 1 no gate, 2 no gate, 3 no gate.
No gate.
Yeah, so the answer is D, with no gates. 7. The 2 types of gates which are called universal gates are
And what? And or A.
NAND or NOR. So the answer is B.
B is that universal gate.
Universal gate.
And or A.
A.
Yes.
No. Universal gate. Please turn to page. Turn to page 160. NAND logical and NOR logical are called universal logical.
Oh, universal, but
right? NAND and RAW and NOR. Because the two kind of gates can be used to implement other basic Boolean gates. To implement the other basic Boolean logic.
But sir, basic gate is 3, yes? Basic gate.
Yes.
And or and not.
And or and not are called the basic logic. The basic gate, logical gate.
Yes.
But not called universal gate. Universal gate.
This basic gate is 3. And
Yeah.
gate, not gate, and or gate.
Yes. So the answer is B, NAND or NOR. Okay. Question 8. The circuit shown is equivalent to
A1, B1.
A bar, B bar, A bar, B bar,
Double
bar, bar, A bar, B bar, A bar, B bar.
A1, B1, A1, B1, bar, A1, B1, bar. So, A1, B1. Or gate.
Okay.
Yeah. No. It's or gate.
A bar,
It's or gate. B1.
B bar, and right,
Down. Again, but
and again it was up bar. So it equals
A1, B1.
A bar, B bar, right?
Yes. The X
A bar, B bar. A bar, B bar equals A plus B bar,
Yes.
right? So the answer is the answer is A
Nana Palo D.
D.
It's not
not
good.
the bar.
Yeah.
Yes.
It's not good.
Yes. AND gate equals to AB. XOR gate equals AB bar plus A bar B. Right?
Yeah.
OR gate A plus B. So answer is D. 9. The circuit shown is equivalent to OR gate, OR. A bar or A bar, B bar, OR.
Over.
Or
Again.
and again. So it equals to A bar plus B bar. A bar plus B bar
So A dot B.
equals to A B bar. A B bar. So
None of the.
none of the bar.
This
None.
NAND gate. So
Yes.
none of the.
Yes. 10. During the first 3 intervals for the power circuit shown, the output of during the first 3 intervals, the first interval, the second interval, the third interval. So during the 3 interval is this interval.
Z1.
In this interval. So we must first write down the Boolean expression of this diagram. A bar or B.
A low,
A bar or B.
B high. A low, B high. This position. This
A bar
C high.
or B. A bar or B, and C or D. C or D, right? And C or D. And C or D. So the output A bar. A bar.
So
A bar
A
or
low.
B.
That means A low.
A bar low, low.
B have to be high.
Mm.
High.
Oh, so the answer is G1 and G2.
Not.
The output of there for the half circuit down. The output of G1 is low and G2 is low. G1 for this A bar equals to 1.
Yeah.
And B B
0.
0. But A bar plus B equals 1. 1 and C and D. C 0, D 0. So
1 times 0 is 0.
0.
So it's low.
Is 0. So G1 is 0. Oh, G1 is 1. G1 is high, right? G1 is high because A bar equals to 1. Equals to 1. It's hard. It's hard for this question. For this time, for this interval, A bar equals to 0, but B equals to 1. So this equals to 1. For this interval, A bar equals to 1, B equals to 1. So A bar plus B equals to 1.
Yes.
For this interval, A bar equals to 0, B equals to 0. So
0.
Is 0. Is 0. Is 0.
High G1 is high, G2 is low. That's C. G1 is high, G2 is low.
1, 0. 0, 1. So the first three interval is the first three interval is the first interval is big, the second interval is big, and the third interval is big. So in the three intervals, the output of G1, the output of G1 is high or low?
High.
Yeah, high. Because A bar equals to 1. B equals to 1. B equals to 1. So G1 is high. And G2?
It's low, sir.
C. 0.
C and sub C.
0. So
Say
it's
C.
low. So the answer is C. Yes.
Yes.
But the answer of 8 and 9 are C and A.
Can we back sir please take C and A? C, 9 and 8.
Hey, the answer is C and A. Why? Answer of 9 is A. Why?
Yeah.
A bar or B bar.
Mandate sir is
A bar, B bar.
double versus.
Double bar, so it equals A double bar and B double bar. So it becomes AB.
Sir,
And then bar. So it becomes AB bar. AB bar.
NAND bit. The NAND bit, but
So the other is B.
no. If he can write, NAND, so this will be a.
Yes.
Chapter 6.
Okay. That's
We didn't
continue.
continue to what is PPT, isn't it?
Yeah, I have a cut. Okay.
After that, you can actually.
I will convert the PPT to the WeChat logo. Then chapter 6.
That we use Marcus,
Yeah.
who is what sir? 14 point.
From 10 minutes.
Okay.
10 minutes. So we continue to learn chapter 6, functions of combinational logic. Functions of combinational. Half adders.
Encoder, decoder.
Yeah. Basic rules for binary addition are performed by half adder. Half adder, which accept the two binary inputs and provide two binary outputs. So the half adders don't have carry in. Don't have carry in.
That's sum.
They only
Carry out.
only have carry out.
And sum.
And sum. So the truth table of half adder is like this. Inputs A and B are inputs. C out are the carry out. Sigma is the sum. Sigma is the sum.
1 on 1 equals 10. So the sum is 0 and 1 is carrying.
So from this truth table, we know that
Yes, sir.
sigma is for sigma the output is equal to 1 when A and B are n equal. So it is on XOR gate. And when the carry out equals to 1 when A equals to 1 and B equals to 1. So it is on AND gate. So the diagram, the circuit of the half adder is like this. And we can use this logic symbol to represent on half adder. Full adders accept 3 binary inputs, A, B, and carry in, and provide 2 binary outputs, carry out and sum. The truth table summarizes the operation like this. So there are 3 inputs, and for the sum sigma, the output is 1. When the input is like this, So from this truth table, we can write down the Boolean expression. Or the kind map of the expression. Sigma. In fact, the sigma is equal to a x or b and x or c e. Right? For current map, sigma. For current map, sigma. AB, CE, right? There 1, 1, 1, 1, 0. 0, 1. 0, 0, 1. 0, 0, 1. 0, 0, 1. 0, 0, 1. 0, 1, 0. 0, 1, 0.
1, 0, 0.
1, 0, 0. 1, 0, 0.
Triple on.
1, 1, 1.
Yes.
1, 1, 1. 1, 1, 1. So, how many groups on this kind of how many groups? Listen.
4.
How many groups on this kind of
4, sir. No exam.
Yes. Yeah, 4 groups.
4 holes.
Yes, each one are athletic. So there are 4 groups. Each group has one product term.
It's nice group, sir. It's like a snack, sir.
So the minimum SOP expression is complicated. A bar B bar C plus A bar B C bar plus
A, B bar.
A B C plus A B bar C bar. In fact, it is equivalent to A X or B, X or C E. It is equivalent to this expression. And C out is also on. If the output is C out, then the first one is A bar 1, right? The first one for C out is 0, 1, 1, 0, 1, 1, 0, 1, 1. So the second one is 1, 0, 1, right? 1, 0, 1, 1, 0, 1. And the third one is 1, 1, 0, 1, 1, 0. And the fourth one is 1, 1, 1, 1, 1, 1. Then how many groups on this kind of map? How many groups? Xiaohu, how many groups on this formula? Three? Yeah, very good. One group, two groups,
and left.
and three groups. So the minimum SOP expression for C out equal to, for this group A must be eliminated, right? B, C, and for this group A, C, and this group AB. Oh, CE, right? And the answer is this: AB plus A, X or B, and C. Why? Because it don't use the Kamaugh to simplify the expression. It just write down all the three ones, all the four ones, all the four product terms. Right? Four answers. A, B, C, A, B, C bar plus A, B, C plus A bar, B, C plus A, B bar, C, A, B bar, C, A, B bar, C. We know that AB bar plus AB C equals to AB, right? Right? And then A bar B plus AB bar, A bar B plus AB bar C, right? These two equals this expression,
Yes.
right? And this expression is on X or gate, right?
Yes.
X or gate. So the output carry of the following expression is this.
A is a bit
Okay,
plus
plus is the word.